right? And in one dimension, I can actually do the analysis at higher order. There's a higher derivative test. If it's the case that you have all of these being 0, not that. We don't care about that. That can be non-zero. That's the value of the function. Suppose the second and third derivative and first derivatives were all 0. There is a fourth derivative test, which says that if the fourth derivative is non-zero, and it's the first thing that's non-zero, if it's positive, it's a minimum. If it's negative, it's a maximum. There is such a test. On the other hand, if the third derivative is the first non-zero one, it's a saddle. Because what you're looking at, y equals f of x, if you zoom in on the point, the dominant term close to the critical point is the first non-zero thing in the Taylor series. The same thing is true for functions of several variables. It's just that we only can tackle the algebra. Like, we only have linear algebra to do the quadratic piece. We don't know the cubic. Look, something as simple as x cubed plus y cubed equals to 1 we looked at today. 16, right? Was it 16? None of you knew how to graph that, right? I mean, without technology. But so, because these things are much smaller, we can focus on that. And if you go back to calculus 1, what did the second derivative test say? If that's positive, it's a minimum. If it's negative, it's a maximum, provided you got a critical point, right? Why is the critical point important? Because if it's not a critical point, there's a linear term here. And that is way bigger than the quadratic piece, close to the critical point, close to the point. So as you're thinking about approximation of a function of several variables, first order of business is the linear, well, first of all, just the value of the thing at the point. Second of all, the linearization, that's the next best thing. Beyond that, quadratic approximation. Beyond that, things we don't actually do in the course, because those things are a job. They're not a school topic. Hey, I think this would be better if we had a picture. I promised you more examples, too. Let's see here. How about this? F of x, y, z equals to x squared plus 1 over 1 minus y squared. Find the multivariate Taylor series of that, centered at 0, 0. See here, for example, I have a picture of the red is the quadratic, is actually a graph of the Hessian close to the point for some function. What's in the wireframe is actually the function. So to be more explicit, the function is z equals to sine of xy. I can't see it. The thing in red is xy minus 1/6 x cubed y cubed. That's actually beyond the quadratic. That's actually past the Hessian would just be xy. I threw in the next piece for kicks. And so that red is the graph of all the way out to third order in the multivariate Taylor, the graph of that. And you see, if you're really close to the point of the approximation, it really hangs close to the graph of a function. Like, it's a really good approximation if you're close. And then as you get further away, well, sine wrinkles away from the approximating polynomial. In the same way it happens in 2 dimensions, it happens in 3. Which I think is cool. But there are, like right here is an example of a function which defies, this defies our Hessian analysis. This is just something pretty simple too. It's if I remember right, it's z equals to the cosine of x squared y squared, I think. Is that right, or is it cosine of xy? What was it? Oh, I think it's just xy. So cosine of xy has a graph that looks like this. Now, this one won't be covered by our second order analysis because the power series for cosine is so what's the first term is what? So I suppose that if the function is as simple as this, there's still some kind of like even power series. I don't know what's beyond the standard results, honestly. I mean, you're asking me kind of like what's beyond the course. That's not what you really are asking, but your question drives me to this. I'll try to behave. The point is, the Hessian is 0 for this. But on the other hand, if you just think about it, by common sense, you can see that 1 is a maximum, right? It's cosine. Cosine can't be bigger than 1. So if you reach 1 at 0, 0, that has to be the maximum. Can't be a minimum. And then, so what it is that it's just so flat. It's so flat that even the quadratic piece of the graph is 0 at that maximum point. Let me take a breath. All right, so did you guys figure out how to do this one? Let me put this away. Unless there are questions. No? So here, first of all, like these problems, what you got to think about is, well, how can I just look at it in terms of things that are easy? I mean, your goal is always to break it back down to those standard substitutions if you can get away with it. And so I can just multiply a geometric series times 1 plus x squared, right? Or x squared plus 1, which is what? This is, and so that's 1 plus y squared plus stuff that's more than quadratic. Multiply it out, what you got? You got 1 plus x squared plus y squared plus higher order stuff, who cares? Oh, I don't know why I put a z there. Can I fix it? Make it interesting? I can't. Ha! Ha-ha! Take that. There. Now, this is beyond. I sketched for you how to derive this eigenvector condition for the maximum of a quadratic form in terms of its matrix. That derivation turns out to be valid in n dimensions. If you want, there's a lecture in advanced calculus I did this semester where we do that. So that generalizes. And somehow the calculation I did in advanced calculus was easier than that. But anyway, we have other toys to play with there. So the point is then, I don't really need any kind of fancy algebra to figure out what's going on here. Is f of 0, 0, 0 a critical point? It's a critical value, right? Equal to what? Equal to 1 is a critical value because there's no linear pieces. The gradient of f at 0, 0, 0 is equal to 0, 0, and a 0. Is it a min or a max? It's a min. That's right, because if you go a little bit away from the point, you're taking 1 plus something positive, which is clearly larger than 1. So 1 is a minimum value. I don't need some fancy linear algebra to tell me that. I can just use common sense to look at that and say, duh, right? As long as there's no cross terms, it's easy to think about. Those mixed terms make it hard to think about. What if I take the same example and I change that plus to a minus? What's the difference? Sorry, let me stick with my color coding. What was our conclusion? F of 0, 0, 0 equals to 1 is local min, right? So in this case, what we'd say, it's a critical value still, right? But what? It's neither a max or min. Why? It's a saddle. It's a saddle type point. Although, I don't know where you're visualizing that. I mean, W equals f of x, y, z is like a four-dimensional thing, right? So it's some kind of four-dimensional saddle or something. Well, three-dimensional saddle in a four-dimensional space. How do I know that that's not a max or min? Well, think about it. If I've got a minus here, right? What happens? If I choose z equals to 0, and I choose x and y positive, or negative, whatever, non-zero, I'm getting values a little bit bigger than 1, close to the critical point. However, if I take x and y both 0, and I let values go positive or negative, anyway, non-zero in the z direction, then I'm getting values a little bit less than 1. So if I go in the z directions, if I have a little bit in the z direction more than the x and y direction, I end up with negative values. If I go in the x and y directions but not in the z directions, I get positive values. So it's neither max or min because I can find values of the function close to 0, 0, 0, which are both above and below 1, right? So it's not a relative max or min. You look confused or annoyed. Maybe a little bit of both. I'll take either. I mean, my goal was not to annoy you, although it does give me a certain pleasure. That's true of all students. I'm sorry. Wait a minute. Oh, I'm not supposed to say that. Is that on? Oh, no. It's been recorded. I'll have to edit this out. Who am I kidding? It takes too much time to edit things out. I got another picture to show you. So, when I think about minimization and maximization of a function of two variables, I have a certain luxury, which is visualization in 3 dimensions, right? I can think about the graph of the Hessian. I think about z equals q of xy. I can think about z equals f of xy, and I can actually see what's going on, right? When I think about a function of 3 variables, the closest thing I can get to a graph is a level surface, right? So, come on. So something like, well, something like this is, I can kind of picture it like that. These are level surfaces of a function, an objective function, right? And as you go out the onion, you get larger and larger values, right? It's something like that I have to think about. Or, if I want to think about it, if I've got a critical point, maybe I'm looking at the maximum values of a function of 3 variables on the unit sphere, and then I'm going to come into these different, or I'm thinking about the maximum of the function, I think 1 over x, y, z. These are level surfaces of the function 1 over x, y, z. And these actually are where it would touch, I think, the unit sphere at minimum, like the minimum and maximum values. So these would be like negative level surfaces. These would be positive level surfaces or vice versa. That's the kind of thing I'd have to visualize for functions of 3 variables. You see, so visualization, direct visualization of the 3-dimensional problem gets kind of challenging. But we can still do things with those expressions algebraically. You know, if you've got a sum of squares, it's as simple as thinking about if they're all pluses, it's a minimum. If they're all minuses, it's a maximum. If there's a mixture of pluses and minuses, it's a saddle, and that's all there is to it. Unless there's a mixed term, in which case you need linear algebra, so I wouldn't ask you about it. So, unless it's 2-dimensional, in which case we have the second derivative test. Second derivative test does the linear algebra for you. And with that, I will shut up. See you tomorrow.